right, so let's start here. I want to at least get started here, and then when we kind of go the next point, you have some of this in your head. All right, I don't want to be in red. I mean blue. More common for the students. So if we make values arbitrarily close to the number L by taking x sufficiently close to number A, we can write. So basically, this is one of those fancy things that's been really weird. So we say a limit as we bring x close to A becomes arbitrarily close to this number L. And what does that mean? It means, well, let me show you, right? So let's look at this. It's just easier. It's easier to explain. So after we crunch through some numbers, I'll go back to the definition. So notice here that I cannot plug in 4 because if I plug in 4 down here, I get this. It just doesn't. It won't work. And so what I want to do is get really close to it. And so I'm going to be looking as I get close to 4. Because here, what happens? Let's open up Wolfram Alpha. Let's open up Wolfram Alpha to do this. Hi, let's go to Wolfram Alpha. I'll be using a lot of Desmos and a lot of Wolfram Alpha. So let's type in this happiness. So we have x minus 4 divided by the quantity of x squared minus 7x plus 12. All right, so it looks like this. But what happens when I set x equal to 4? So here I'm going to set x equal to 4. So wherever I see an x, I'm going to plug in a 4. It's undefined, right? So I get nothing. So if I ask you, what is x at 4? This you're going to say undefined. And I says, well, okay, that's nice, but let's pretend we're a bunch of engineers or physicists who say, what's it when I'm close to 4, right? And that's what the limit asks. What is it like when I'm really, really close to 4? Well, in order to do this, let's just slowly walk towards 4. And so we're going to walk towards 4 from the 3 or from the left side, we're going to walk to 3.4 going this way, right? We're going to walk it going this way into it. And walking it going this way into it. Let me open up the walking going this way into it. We'll start at 3.5. So we'll have 3.5 here. We'll have 3.5 here, and we'll have 3.5 here. And that gives us the value of 2, right? And so if I write over here, I'm going to have 2. So let's pick in the next one, right? So 3.75. And so now I'm getting even closer to it. And I get the value of 1.3 repeating, right? So 1.3 repeating. All right, let's do 3.9. 3.9. 3.9. And I get 1.11 for a while, right? And let's do 3.99, 99, and 99. Oops. And I get 1.011. So this is 1.111 roughly. This is 1.0101, right? And a 3.9999. Just add one more set of 9s in here. I get 0.1. Okay. And so as we notice as we get close to this gets really close to 1. Let's go the other direction from like 4.5 in. So let's walk this way. And we'll probably end on this note with this page. Okay. All right. So here we'll have 4.5. 4.5. And does everyone see how I'm typing this in to make my life easier? So I get 6.666, right? So here I get 0.6 repeated. And if I type in 25, 25, I get 0.8. So this is 0. Oops. 0.6. This is 0.8. And let's just do the last three real quick. All right, so we have 4.1, 4.1, and so I get 0.90909, and if I do 4.01, 0.01, 0.1, I'm getting 99009900, and if I put in 0, 0, 0, I get 9990000. So here we're going to get 0.90990. Here we get 0.990099. And here we get 0.9990009. Okay. 9. So you believe me that I say, even though it's undefined at that point, right? Because we cannot have x equal to 4 because it's undefined because I have 0 on top and 0 on the bottom, so that's undefined. It has a hole right here in our graph. You would believe me that the limit, and we call this the limit as x approaches 4, right? So as x gets close to 4, not at 4, of my function, we're going to say this is equal to 1, right? Because it looks a lot like 1, right? This is the closer I get, the more it looks like 1. The closer I get here, the more it looks like 1. And so we're going to say as we get arbitrarily close to our value, right? So if I'm plugging in, I want to find out what f of a is. So we really want to know what f of a is. Well, f of a doesn't exist, or there's other problems, right? There could be a lot of problems. But I want to say, what does the function kind of act like it's going to go to? And that's going to be our L. So L is going to be the number we're going to get arbitrarily close to. And we're going to start by getting really close to moving x close to a. So we're going to say the limit of the function as x approaches a is equal to L. Basically, it's a way of saying it never gets there, but what does it act like it's doing? And then here, it's act like it's going to this. All right. Well, that is the end of class. I flip over. All right. So let's look in. All right. So let's look at this. Now let's consider a slightly different function. So assuming we have the piecewise function shown here, does the value of the limit change? So now as we walk function values in this way, right? And as we walk function values in this way, is that limit going to change as we look at it, right? AKA, as we walk these values, are they going to change at all? Yes, no, maybe? Anyone have a guess? No, it's not going to change. That's correct. And so, no, it's really not going to change. So here we have, does the value change? No, because and the reason is we don't care. We don't care. Oops, hi. Care what the value is. Oops, hi, this thing's having a little bit of a lag. Value, actual, I'll just write really. Really is at 4. So we really don't care what it is at 4. So no, it doesn't change. All right, so let's look at this. So when an electrical circuit is turning off, we see a jump, right? In the electricity route. This is a very simplified version of instantaneous rate of change. This right here is called a Heaviside function. Heaviside, I think it's spelled this way. This is the Heaviside function. And so you'll see this a lot where it's just always one value, and then all of a sudden it's 0, and then all of a sudden it's one value at a certain number. Okay, so this is called the Heaviside function. Given in the figure below, can we determine this limit? And so let's look at this limit real quick. So a v of t. So let's look at the limit of v of t. So as I'm walking this way, right, I'm going to do these notes slightly out of order because I realized that page 3 should be page 4. Just when I was reviewing, prepare for this. So we'll do this page and then we'll do 4 and then we'll come back to 3. So notice as we walk in from this side, what does the limit look like? What is our limit? You know, of v of t look like when we put in the values of, like, I don't know, say 4.5. Well, here the function value of v of t of 4.5. Oops, I'm going to have to get rid of some of these pages. I'd loaded too many at once. 4.5, well, that's 0. Well, what's it at, like 4.9? Again, it's 0. I can zoom out just a little bit for you guys. There you go. So here, this is 0, this is 0. So this looks like it's going to 0, but here if we come from the other direction, let's say at 5.5, this looks like 2. And here if we go from this from 5.5, this also, or 5 point, not 5, but 9, this also looks like 2. And so here, as we're walking in from the left side, it looks like 0. If we're walking from the right side, it looks like 2. And so we really can't, it's not really converging to a number, right? It's not getting arbitrarily close to a number. It's actually getting, in this case, arbitrarily close to 2 numbers. And so in this case, we're going to say the limit, I'm going to write, we'll just put it right here, d n e. And d n e stands for does not exist. Okay, so it does not exist. All right. Let me quickly just export this so it gets less chunky. I don't know why my computer's being so chunky today. Boop. And so we say it does not exist. All right. I'm going to actually close out this window real quick. That way we'll open up more space on my computer. Hit 2 and save. Do page 3 real quick. All right, so there's not too much to write here. So it says if we make our values arbitrarily close to a number by taking x sufficiently close to a value less than a, we write the limit of a, and then we put the minus sign as like a little power. Let me like zoom on in a little better. Let me zoom on in a lot for those who are watching on a phone. We make this minus sign a little, and we put this null, and that means we're coming, and we say the limit of f of x as it approaches from the left. And so we say this is a left-hand limit, or a left side limit, or the limit from the left, okay, is equal to L. And so in a case we just showed, we said the left-hand limit as we walked in was 0, right? And the alternate notation is this. We can write f of x goes to L as this goes there. If we come arbitrarily close to, so basically for numbers of values strictly greater than, we write f of a and we put a little plus sign up here. And that means we're approaching from the right. And we said the limit of x approaches from a plus is, or from a positive. And so we say we're moving from the right. And so from our previous example, it looked like 2. So in order for a limit to exist, f of x has to exist for both f of x limit of a positive, right? And they must be the same value, right? And so the problem is in our last case, I had to throw it away, didn't I? Just to create the space. Let me just open it right back up. I have it right here. Saved it. So now let's look at our last case real quick. Our limit doesn't exist because as we're coming in from the left here, we get 0, right? And that left-hand limit is 0. And we come in from the right, it's 2. For the limit to actually exist, these have to agree, but they don't. This looks like 0, this looks like 2, so it doesn't exist. So we say I do not exist. So let's look at a different one real quick and show you by another example. Is that the Heaviside function below the graph? It's a type of Heaviside. So a Heaviside function is a classification of functions. It's where it's always 0 and then it all of a sudden clicks on and then it's always some number. Depending on your book's notation, or whatever book notation you get into next time, it always changes how they define it, right? We'll redefine it later though, but that is Heaviside function, yes. Some books strictly define Heaviside function to be 0 until 0 and then 1 from there on afterwards, and then they just do transformations on that, which is fine. And some books classify a classification, and they'll have like Heaviside 5 or something. They're all the same. It just depends on what your book does. We'll deal with that more later. I just wanted to show it to you now. Okay. All right. So here, let's look at this one. So this is something we can easily graph because we learned from our section of things that this is the graph of this function here. So here, if I'm coming in from the positive values, what is this graph? What is the function of f? What is the limit as x approaches from the right-hand side of the square root of x? What does that look like? What does this one look like? If I'm just coming in strictly from the positive values, you guys know what value that would be? Yeah, 0. However, if I would come in from the limit of x, strictly looking at the negative values, well, here I see nothing, right? The function doesn't exist. It's undefined for the whole thing. So this does not exist, right? And so here in this case, it doesn't, the actual limit does not exist, right? The actual limit here does not exist, okay? Because we can't say it's from both, all right? Now, could we say this limit exists and can you calculate it? Yes. So if you just wanted strictly the limit from the right-hand side, or the positive value, you can find that, but the other two do not. While we're here, let me mention this briefly. Your book mentions this, we go over this, but unless you're doing really hard limit proofs, you don't need it. And since we're short on time, this is something I have to teach in person because I actually wave my hands around like a crazy person. Just how you teach it. However, in this, they also give what they call the epsilon delta definition of a limit. Let me just write that right here. So the limit as x approaches a for some function x to equal L, they say, hi, I didn't ask for you, sorry. Why wouldn't the last one exist again? Oh, because it needs to happen for both this and this limits must exist. So this one does not exist, right? And they have to have the same value, okay? All right. So here, let me show you the epsilon delta definition quickly. So basically it says for every epsilon, so this is an epsilon, it's a Greek letter, E, greater than 0, there exists a delta that is also greater than 0, such that as we get arbitrarily close to our desired number A, there's a delta, then we'll be arbitrarily close to our limit. So this is called the epsilon delta limit E epsilon. So what is this basically saying? So given an epsilon, I can find a delta such that I'm so close that this limit, whatever the x's I choose here, right? This will be so close to L, it would be smaller than this number. Okay, so this is what they call the epsilon delta definition. So basically, see if I can describe it. Let me see if I can just really quickly describe it. So here, let's just say I want to choose, I say epsilon is like 0.5, right? And so here I draw 0.5 above it and 0.5 below it. That means if I choose a delta here of like 2.5 or 2.5, I can go this far above it and still be within the range I want to be. Okay, don't worry too much about it. This is the if you're really doing proofs and you really get into advanced calculus, yeah, you'll be doing epsilon delta definitions, since that's the only way you prove limits later. But for this class, let's just not crunch too hard on it. All right, so so kind of write this down, but don't worry too much about it. In fact, if I don't see it in the notes you turn in, I won't cry. Okay. There's an example in the book. Go over it, but I'm not assigning questions from it, so you should be fine. All right, so let's look at this. So let's look at it graphically. So we can look at these via graph, but I want to look at two of these graphically per se. So do we know how to do this without a graph? And the answer is not yet. We'll do that the next section. Without a graph, we can do that. We can just, but with a graph, we can kind of guess what it is. All right. Is there a limit on the y value? I'm not quite positive of the question. And what's the scribble in Q3? I'm not positive where Q3 is. Oh, you probably mean the third part. This is D does not exist, so this is the limit of x. As x goes to 0, does not exist. Is there a limit on the y value? Oh, I see what you're saying. Can we do limits in the y thing? Sure. When you get into 2D limits, so basically it doesn't matter what this x is. Let me answer this question real quick. It doesn't. Let's go up. So as we take limits, if this is an h, as h approaches a, we'll have some function of, or we could have like g of h, right? So then the letters don't matter. So if in one dimension, we're fine. Once you get into limits in 2 dimensions, it gets complicated, to say the least, and you'll have a limit in the x as x and y approaches a pair of numbers. Okay, so that's what happens with the y value. So the limit is always as your inputs approach some numbers and the output equals something. Okay. All right, so let's look at this. Let's do this in Desmos because I'm not positive you guys know how to graph that by hand. All right, so let's just open up Desmos real quick. Let's definitely not have our attendance up. All right, well, I'm going to save this. We're going to want this later, but let's just go ahead and type in sine of x divided by x. All right, so here's the graph of sine of x divided by x. And let's kind of zoom on in. Now, what is the value here? So we're going to try to find this at, oops, I did not switch that. What's the limit here? We know exactly what the limit is here. We can calculate it. Let's make these 0, guys. I did not switch that when I moved it over. So the limit is x goes to 0. Now, if I plug in 0, I'm going to have sine of 0, which is 0 over 0, which I can't just directly plug in. However, if we look at the graph real quick, what does it look like it's going to? It looks like it's going to 1, right? And so, indeed, that's what it is. Now, we'll prove this one later, but here, the graph, it kind of goes, oops, let me zoom out so I can draw this correctly. Zoom out, zoom out, zoom out. So here it comes in at 6. Comes in, comes down, comes up, hits 1. And so, oops, let me just draw this a little bit better around here. And so, oops, I'm on the wrong layer. And so here we can see around here, as we come in from this side and as we come in from this side, it indeed looks like 1. All right, so let's do this again as x approaches, but now we're going to have sine of pi. Oops. I just made a bunch of mistakes on this, didn't I? I'm going to have sine of pi over x. I wanted to do this one. So let me show you what I really meant to type in. So we're going to look at sine of the quantity of sine of pi over x. Sorry about the couple of mistakes on the notes. So what do we have here? Well, we have a big mess, right? And as we zoom in, does the mess get any better? Absolutely not, right? We just have a huge mess. And so what's happening here as I get sufficiently close to zero, this number is exploding, right? And as this number explodes, it just oscillates faster and faster and faster and faster and faster. And so in this case, between 1 and negative 1, right? So between 1 and negative 1. And so this oscillation, so as we get sufficiently close, it just never gets any better, right? It just absolutely never gets better. And here's something where the epsilon delta definition comes in. But notice here, as we get, seemingly close, we're just still no better than we were before, right? And so in this case, if it oscillates infinitely, because even though it looks like it's the two values done, it's not like we assume it's continuous, kind of, right? But since it oscillates infinitely, it's not really continuous, but it looks that way. And so here we just say it doesn't exist because it doesn't really kind of crash into a single number. And it kind of goes like this, really crazy. And then it comes back out. And so we just say this one does not exist. And so if you see this over oscillation right here, you're just going to say it doesn't exist. Okay. Let me rewrite this real quick for you guys. This is the limit as x approaches 0 of sine of pi over x. Sorry about that. I just need to triple check these things. All right, so let's go ahead and save this. All right, export as PNG, and then we'll close it out so we have room. And yeah, don't skip, we don't need it. All right, so let's look right here. So let's do this for a second. And we may not do all of these, but I do want it to have enough to choose from. Can we go back to example 4 real quick? Wait, what's the top limit? The top limit was 1. Wait, what did you do the 4 after the x? Oh, we switched it here. Let me reopen it and show you guys. Oh, here we go. So here we switched it. So we're taking the limit. I left it as 4. That was just a mistake in my coding of this. So here is the limit as x goes to 0 of sine of x over x, and that's equal to 1. And here, for this one, it does not exist as the limit as x goes to 0 of sine quantity of x of pi divided by x. Okay. All right. Try to keep up, because if I keep going back, I'll get in trouble because we'll run out of time. Just how it's going to work. All right. But I'll try to give a break. That way you can finish writing. Okay. So here's a whole bunch of things. And so here we're gonna, this is the same graph twice. I just put it so when I was zoomed in, I had it twice, right? And so let's just do a whole bunch of these, just an obscene amount of them. All right. So what's the limit as we go to, so the limit here, what's this limit of QT as we come to -6? Well, here's -6. If I come in from the right side and left side, it agrees to the same number, which is 0, right? Well, what is the value? I'm just going to go this way. So what's the value at 0? The value at 0 looks like to be 1, right, according to my graph. So it's just 1. Or no, that's not 1. That's a 3. What's QT of 4? So this is the -4, right? And I'm coming in this way only from the left side. And so here this means QT. So if I'm coming in -4 to the left side, it looks like -4. Here, if I do Q of t, and I want to find the limit at 1. So here I'm finding the limit here at 1. So if it looks like I'm coming in from the left side, it looks like 2. If I come in from the right side, it looks like 2. And so this one exists, and it's 2. Now, what's the value at 1? Well, the value at 1 is actually fine, right? It's actually what the value is. All right, so let's look at 4 if I come in from -4, I want to find -4, but this time we're going to come in from the positive way. Well, this still looks like the same value. So that looks like -4. Any questions on these first 6 I've done? Why one number is a number, one's not? No? Okay, so let's keep going. So here we have this is equal to 4, -4, and this is equal to -4, then the limit itself does equal -4. What's the value at -4? Well, the value here at -4 is also -4. So here, if the limit and this agrees, we say it's continuous around that point, and so it's continuous at this point. We'll get into continuity later though. All right, so let's go here. Let's do -2. So -2. So what's the limit as I come in from -2 from the left side? So here, if I come in from the left side, it looks like it's -3. But let's look at it from the right side. If I come in at the right side, it looks like it's only -1. So what's the limit as I come into -2? Well, this one does not exist. Why? Because this limit and this limit do not agree, right? So they're not agreeing, they're not the same. So that does not exist. What's the actual value at 2? Well, it also doesn't exist. See how I have an open hole here, an open hole here, and no other point. So that one just, and so it's not, this one does not exist. This is actually undefined. I guess that's, if I was going to be correct about it, just not defined, right? So it's undefined at that point. Let's look at the limit at as t goes to as q goes to 0. So it's 0. So here, if I come in from the left hand and the right side, it looks like it's 3. So this one is 3. And let's just finish this real quick. Let's do +2. All right, so what's the value when I come in from the left-hand side for this? It looks like it's going to be -2. So this means come into 2 on the left-hand side, okay? Here, if I come on 2 on the right-hand side, from the right side, or from the positive side, I guess, here it looks like -2. Now, does this limit agree with this limit? No, so it does not exist. Now, what's the actual value at 2? Well, it's right here. It's filled in this dot. And so this value at 2 is -2. Let's just do the last little set here. If I come in from 5, so here the limit is I'm looking for 5 right here. If I come in this way, it looks like, what does this value look like? Well, it looks like -2. If I come in from this side, it doesn't exist, right? There's nothing here, right? But the actual value does exist at 5, and it is -2. And so here, this is just a way of graphically going to the answer tree. What's the difference between undefined and does not exist? Undefined means there is no definition for it, does not exist. I'm splitting hairs for a little bit. Undefined means it's something I couldn't even compute. Does not exist as I compute it and it fails. Because the function is not defined outside. Because so this function has no definition. It has nothing. There is no value at 2. There is no value at 2, right? There is not a value at 2, right? And so that means the function is not defined at 2. But if the limit, if the function is not defined, this limit is defined, right? It's we're splitting hairs in math. There's a large difference from not existing and not being defined. This is well defined, it just doesn't exist. What's with the positive and negative signs? Oh, right here? These signs? Is that what you're talking about, Sierra? Yeah, it means from coming from the right or the left side. So remember from our little notes that here I put a little negative sign up here that means I'm coming from the left, and this means I'm coming from the right. Okay? And so it's just which way you approach the number. Okay? All right. So the next section is a doozy, and so we better get to it.
Professor, I have a question.
Yeah, go for it.
How do you know which line to look at?
Which line?
Like, because there's three lines there with all these dots, and then, like, if you look at, um, like R, so going to 5 from the left, like, Wait a minute.
Okay, yeah. Let's do this. Let's do this. I know exactly what you're talking about. So let's look at R real quick. Hi. Hello. My computer died on me. Wakey wakey computer. Hi. Undo all that. So which of these three lines exist? So here we're looking at 5, right, for R. So here we just want to look arbitrarily close to 5. And so here we're at x equal 5, right? Here's our x equals 5. And so we were going to look at this line right here because we only care for things really, really close to it. This is pretty far away. This is pretty far away. And so we're only caring about what's really, really close for it. The same for, let's do the same for like -2. For -2, right, here, when we're looking from the positive side, we're only really looking at this line because from here on, it's the function value for the positive value, or from values which are slightly greater than 2 or -2, right? Here, for this one, we're going to be looking at values which are slightly less than 2. So we're just looking right here. And so when you do these limits, you kind of need to put on blinders. You're going to like, well, I don't care about the rest of the function. You're just going to like, I only care about this, right? Or I only care about this. You're going to really just need to focus in on the small little part that's next to it. Does that answer the question?
Oh yeah, that makes much more sense now. Thank you.
Okay, please ask questions. Please, please, please. All right, so let me put another star here. So we'll add that. Okay,